Good afternoon. Hello, everyone. Thank you for joining us today. My name is Jason Burwen. I am ESA's Vice President of Policy. Thank you for attending today's webinar on enabling energy storage to reduce greenhouse gas emissions. Today's webinar is being recorded and will be available at www.energystorage.org. Your participant lines are going to be muted throughout the webinar. We do welcome your questions and comments, of course, which can be submitted at any time via the chat box on the left side of your screen. I will be moderating those questions to bring to our presenters in discussion today. Following the webinar, you'll receive a link to the recording and slides, as well as a brief survey regarding today's topic and topics for future webinars. I encourage you to please give us your feedback so that we can ensure ESA continues to provide the highest value information to you and your organization. So it gives me great pleasure today to introduce our speakers, obviously besides myself as the Vice President of Policy for the Energy Storage Association. We're pleased to have with us Eric Hittinger, the Assistant Professor of Public Policy at the Rochester Institute of Technology, Ted Coe, Director of Policy for STEM, and Elizabeth Knoll, Deputy Director of Congressional and External Affairs in the Climate and Clean Energy Program at the National Resources Defense Council. Before we begin today's presentation, though, I'd like to remind you that registration for the 2018 Energy Storage Studio Conference is now open. Produced in collaboration with the Electric Power Research Institute, the Studio Conference is designed to examine the steps necessary to successfully integrate an energy storage project and evaluate the ways companies are deploying storage to lower costs, reduce emissions, and establish a more resilient grid. The conference is going to be held in Charlotte, North Carolina on October 16th and 17th. For more information, please visit energystorage.org/storagestudio, all one word. And I really encourage you all to make it out. This is a rare opportunity where folks are really going to be talking about how to really integrate these projects into the grid and do that work better. As a reminder, of course, for those of you who are not as familiar with ESA, ESA works to accelerate markets, connect members, and educate all stakeholders. Our members directly influence our educational programming, such as this. So if you'd like to learn more about membership value and opportunities, please contact Membership Manager Richie O'Neill. His information is on the slide in front of you. And without further ado, it gives me a great pleasure to hand over the microphone to Eric Hittinger to begin today's presentation. Eric?
Okay. Hello, everyone. Thanks for inviting me. It's great to talk to energy storage professionals about some of the work that we've been doing on storage. And what I'm about to show you is actually a rather fast summary of 4 different research projects, all of which have been supported by various NSF grants. And all of them have been focused on the topic of what happens to electricity system emissions when we add energy storage. So getting right into it, all of this was inspired by a few basic questions that we had several years ago, looking hypothetically at could energy storage decrease or increase electricity system emissions? And we came to this and said, actually, we were concerned that at least in certain places, storage might actually increase the emissions of the electricity system. So we all know, if you have bulk energy storage, you're moving a lot of megawatt hours or kilowatt hours, you're probably going to want to charge up at night when demand is low and prices are low, and you're going to discharge at peak time when demand is high and prices are high. Whether that's driven by a desire to reduce peak demand or level out prices or just make money, you'd have a similar charging and discharging effect. But if you look at what the marginal generator is, the marginal generator is that generator ramp up to increase its output to meet an increase in demand, or a generator that would ramp down to decrease its output if there is a sudden decrease in demand. In some places in the U.S., at nighttime, when demand is relatively low, the marginal generator can be a coal plant, although this is becoming less true over time. At peak times, the marginal generator in most places in the U.S. is usually a natural gas plant, if it's not something like an oil plant. But of course, if you use storage to charge up from coal and displace natural gas generation, you would have a net increase in electricity system emissions. The second effect is the effect of the inefficiency of storage. So no storage is 100% efficient, so you actually lose a little bit of energy along the way. So whatever your the emissions are of your charging and discharging energy, your charging energy actually needs to be somewhat cleaner than what you're displacing in order to just break even. So the inefficiency of storage can actually hypothetically make this worse. Well, that's all fine in theory, right? That's just a theory on paper, but how does it work out if you use actual electricity price data around the U.S. and actual emissions data? So we went out and took hourly electricity price data from around the country, and we got marginal emissions rates that are based off of the measured emissions from power plants from the EPA eGrid databases, and we used that to calculate what the marginal emissions were of different power plants during different locations, different times of year, and different hours of the day. And we put all that into a model of storage trying to buy low, sell high, and then figure out what the emissions effects were. And what we found was that consistently across the U.S., at least for the year 2012, so this is a backcast data, because we use real measured data, we of course use data from the past and can't make a projection, but in the year 2012, we found that if your storage is about 75 or 80% round-trip efficiency, you consistently would increase CO2 emissions across the U.S., even in the relatively clean places like California and New England, where the off-peak power marginal generator is never a coal plant, but it just wasn't cleaner enough than the peak power plants to actually be a net reduction in emissions. In the dirtiest places like the Midwest, you actually increase emissions to the tune of about a couple hundred kilograms per megawatt hour. If you compare that to the emissions from a coal plant or a natural gas plant, it's not trivial. It's less than both of those, which is good, but it's not trivial either. So we did this work looking at just storage on its own, but we also wanted to think about what happens if you have storage and renewables. And if you've thought about this question a bit, how to operate a storage and renewables plant, you relatively quickly realize that the renewables have their own emissions effect, and the storage operation has sort of a separate emissions effect, and you can basically model them separately. So a lot of people come at this and don't quite believe that argument, and hopefully I can convince you here that the effect that I just described still holds even if you charge from renewable energy. So consider these two scenarios. One, you have a solar power plant that produces 100 megawatt hours at noon. You could put it onto the grid at noon, and it'll displace 100 megawatt hours from whatever the marginal generator is at that time. So let's imagine that the marginal generator is 500 kilograms per megawatt hour, so therefore the emissions benefit of solar is those two numbers multiplied together, and you save 50 tons of CO2. Great. You could also store that solar energy and discharge it at 5 p.m. Let's say that your storage is 80% round-trip efficiency. So therefore, at 5 p.m., you displace 80 megawatt hours instead of 100 from whatever your marginal generator was at 5 p.m. And let's say it's also a little less efficient, it's a little dirtier at 5 p.m. It's 550 kilograms per megawatt hour. In that case, the emissions benefit of the stored solar is actually 44 tons of CO2. It's actually a little bit less, even though it's displacing a dirtier generator. And that's partly because of the inefficiency of the thing. But the real point of this, you could tweak the numbers and say, well, the marginal generator might be higher than that, or my round-trip efficiency is different. But the point is that you can't claim that storing the solar gives you zero emissions energy, because that solar could be used to displace something else when it was produced. Of course, you might say, well, hey, maybe that solar would have been curtailed at noon, in which case I completely agree. If you are storing energy that would otherwise be dumped, then of course it's a free lunch. It's an absolute victory as far as emissions are concerned. And of course this will be an increasing problem in the future. So in areas where there is a lot of curtailed energy, we can expect that storage will have a really beneficial emissions effect. Of course, if we build new transmission to keep up with the curtailed energy, then that would start to eat away at those potential savings. Anyway, one of the objections to the first work that we heard, which I considered very reasonable, is that energy storage is a great technology for enabling new renewable energy. You can put on more wind and solar if you add storage to the grid, which is certainly true, but it is pretty hard to estimate what that effect would be. So instead of working out what the effect of storage would be, we used our existing results and said, well, how much new wind or solar would you need to add, would storage need to induce before it was considered an indirect emissions benefit? So this shows our results for wind, and it shows how much new wind you need to add per 100 megawatt hours of storage, or 100 megawatts of storage, or you could pick your favorite units. This shows that you don't actually need much wind to be added. So if 100 megawatt hours of new storage, which is quite a bit of storage, pulls in 2 to 4 megawatts of new wind, then the storage is a net emissions benefit. For solar, the numbers are higher. It's between 5 and 15 megawatts of new solar are needed per 100 megawatt hours of storage. And these numbers are higher basically just because a given megawatt of solar produces less renewable energy than a megawatt of wind. It has a lower capacity factor. This is the basic reason why these numbers are lower. And so this means, importantly, that any renewable plus storage project, if you consider the project as a whole, even though I kind of just made an argument that you shouldn't, any renewable plus storage project will reliably decrease emissions. So if you look at existing and proposed projects, they tend to have a scale of storage that's equal to or smaller than the scale of renewable energy, and those would be reliably decreasing emissions. So for example, the Pathfinder Wind project, which is was a proposed epically large wind plus Ks project, if that was built as proposed, our analysis suggests that the wind plus storage project would reduce emissions 93% as much as a wind-only project, so almost as much. And if you can argue that that project would only get built because it would only get built if the storage were there, then it would be a huge emissions benefit to have that storage. And another example, we had the storage mandate in California, 1.3 gigawatts. If that induces more than 325 megawatts of new solar, then that mandate also has a net emissions benefit. So everything that I've shown you thus far has been based on backcast measured data from the past. But of course, in the future, one of the things that we all expect is to see a lot more wind and solar getting built, which ought to change the game for both the economics of storage as well as the emissions effect of storage. So to investigate this, we asked the question, well, if you add enough wind and solar, storage will reduce emissions, but when do we hit that point? So we did a big dispatch model of the Midwest ISO. And so on the left here is 1 day of operation of the Midwest ISO, where natural gas is in gray and coal is in black, and they're stacked up from cheapest to most expensive. And if you add storage, it tends to charge at that 5 or 6 a.m. point in time. It tends to charge from coal. And what it displaces over around 3 or 4 p.m. is natural gas. So that's the current status quo of the system. And on this day, adding storage would actually increase emissions. However, if you add a whole lot of wind on the right-hand figure, wind is the blue region at the bottom. You can see it gets windy at night on this particular day. On this day, storage actually charges up from a relatively efficient combined cycle gas plant and displaces less efficient gas and some coal plants and actually start to reduce emissions. And when we calculate this out for the entire year, we found that when we estimate how much new solar and wind you need to add to Midwest ISO, we found that right now storage probably increases emissions in Midwest ISO, but once it hits about 20 gigawatts of wind and solar in total, then it will start to decrease emissions. Now 20 gigawatts sounds like an awful lot, but I would point out that Midwest ISO is already at about 15 gigawatts of wind. And so it's actually not that much further from this point. We estimate storage will start to decrease emissions. And furthermore, if you had any kind of carbon price, it will rekajigger the dispatch stack. It will make coal further up on the stack and natural gas further down on the stack, and it makes it far, far easier for storage to have a beneficial emissions effect. So that's one of the best things you can do for storage related emissions, is to have a carbon price. We've also done some calculations for grids without much coal, like New York or California, and found that if storage can get a couple % of its charging energy from renewables that are being curtailed, then it tends to be an emissions reducing change onto the grid. The last thing I wanted to talk about was a paper where we said, look, everything we talked about thus far assumed that storage is just there to make money, buy low, sell high. But what if storage started to change its operation in order to strategically reduce emissions by trying to charge when the marginal generator had lower emissions and discharge when the marginal generator had somewhat higher emissions? And we did this by making storage consider different, what we called carbon values, ranging from 0, where storage just pays attention to electricity price, to $1 million a ton, basically an infinite amount, where storage basically only pays attention to the marginal emissions rates and tries to reduce emissions, and various points in between. And when we gather all the results from this and put it on a plot showing change in emissions on the x-axis versus change in storage revenue on the y-axis, and this is for 3 different regions, ERCOT in Texas, California at the top, and New York upstate in the middle, we found that storage is pretty easily able to rearrange its charging and discharging schedules. It has very little effect on storage revenue for quite a while. These lines are all flat and go down to the left for quite a while, but you can greatly reduce the amount of emissions induced by your operation at little cost. So across the U.S., this is just 3 regions, but across the U.S. we found that by slightly rearranging your schedule, you could reduce CO2 emissions on the grid by about $15 per ton across the U.S., which is actually rather cheap. And this importantly assumes no change in the grid mix or even in the operation of anything else but the storage, which both would make storage-related emissions much lower if we could get changes in those. And as I mentioned before, if we had a system price on carbon, that would tend to eliminate this emissions effect of storage completely, because that emissions would be internalized into the cost of energy. So in my view, people a lot of times ask, well, what kind of technology is storage? So I view storage as a really valuable technology for improving the operational and economic efficiency of electricity systems. And storage fundamentally provides flexibility, and it helps us to better use whatever resources are available on the grid. That's what storage is really good at. It's not fundamentally good at reducing emissions, at least not on its own. But if we want it to, storage absolutely can help reduce emissions. But I like to point out that that won't necessarily happen automatically. We have to ask storage to do that, or prioritize storage for that purpose, and pay some attention to where and when and how we use energy storage. Certainly able to do that, but it won't do it automatically on its own. So anyway, so that's everything I have. If you are interested in this research, I have 4 research papers on this topic. You've just gotten a taste, but you can contact me and I'm happy to share them or answer more technical questions that we don't have time for today.
Great. Thank you, Eric. And before we move on to our next presentation, we're going to pause briefly to take a few questions that came in during the presentation, really just to focus on some clarifications on the materials. We're going to have a larger Q&A and discussion after all speakers have gone. So we'll just cover a couple right now. Eric, if I can just sum up, I think, some of the high-level takeaways you have here before jumping into them. You're looking at, there's definitely ways in which storage can be increasing to greenhouse gas emissions or reduce the amount of reductions you can get just based on the round-trip efficiency issues and the extent to which it is time-shifting more emissions-intensive resources. You also are finding that it takes perhaps a modest amount of additional renewables or other zero GHG resource deployment to offset that, as well as a recognition that interactions elsewhere in the bid stack, particularly the relative prices of coal and gas, certainly make a significant impact. And finally, to look at how very modest pricing on emissions would lead to a pretty significant drop in emissions from storage operations just by very simple changes to operations. Does that sound like a rough overview of your takeaways?
Yeah, sounds correct to me.
So we've got a few questions in. First question, how would these effects change with greater than 100% round-trip efficiency if such a technology existed? This sounds like someone who's thinking about perhaps certain types of thermal storage ops. And I'd add to that just maybe a larger sense of your first study was a 2012 mix with 80% round-trip efficiencies. If that's updated to current mix and higher, the round-trip efficiencies we're seeing amongst folks in the industry, how does that change? What's the order of magnitude?
Yeah. This sounds like an ice energy question. So good question. We found that the effect was partly to do with the round-trip efficiency and partly to do with the grid mix and marginal emissions rates. So we actually calculated everything at different round-trip efficiencies. So at 100% round-trip efficiency, the cleaner areas, California, New York, New England, storage decreases emissions. So if you put in storage with 100% round-trip efficiency, even back in 2012, and things have been slowly improving since then, but even back in 2012, storage would actually reduce emissions in those regions. But in places like the Midwest, it would have still increased the emissions because, it's the coal charge. If you charge with coal, which you normally would at night in the Midwest, it's hard to overcome that even at 100% efficiency.
Great. Next clarifying question, someone asks, first clarify, was the first analysis conducted on a state basis and not an RTO or organized market level? And if that's the case, can you explain how state variations differ within the same wholesale market?
Yeah, good question. Let's see if I click back. So going back to that slide, we've been doing all this analysis on an eGrid subregion basis. So there's the 26 eGrid subregions, which have these. Well, you can see the boundaries here on the screen, and they are not quite RTO based, but somewhat similar. And we did that because the study focused on emissions. We had it focused on the emissions regions. It was a little bit of a challenge to say, okay, well, what are the prices? I'm using finger quotes right now. What are the prices for the California region? When, as most people here know, California has a bunch of different prices. It was especially challenging in some regions, like the Pacific Northwest is all one giant region in the eGrid emissions data, when it's not really one region as far as prices and RTOs go. So we did have to choose a representative location for each of the eGrid subregions. So the mapping isn't perfect, and basically we had to make some accommodation because the boundaries of the prices don't really match the boundaries for the emissions, and we went towards sorting them by eGrid subregion rather than RTO.
Got it. All right, one last question before we move on to our next presenter. Question asks, does the emissions analysis account for line losses of central generation and line congestion losses during peak periods? This might be someone who's thinking about storage that is maybe located closer to load. I'd also just add to that maybe, are there other system efficiencies like, for example, reduced thermal generator cycling and start-stop that are factored into these analyses? If not, what's the significance of including, say, avoided line losses or reduced generator cycling on that greenhouse gas result?
Yeah, it's a great question. So the short answer is mostly no. Those are mostly not included here and would obviously be additional benefits. Although I think You could somewhat say that the transmission losses are included here because of the way that we get the data. Because it's all just measured data, like what are the emissions from power plants during this hour and what are the prices during this hour. Because it's all actual data, the emissions of power plants and the total amount of energy that power plants need to make in a given hour is already itself a function of the line losses. So it's measured rather than modeled data. That's sort of implicitly included, but we didn't explicitly calculate for any of the other losses, especially things like downstream T&D losses. I guess really distribution system losses, which would be an additional benefit.
Great. Thank you, Eric. All right. I know there are more questions, but we need to pause now to move on to our next presenter. So I'd like to invite our next speaker, Ted Koh of STEM, to please take the microphone.
Great. Thanks, Jason. And thanks, Eric. That was very useful, very great presentation and useful. Going into this, what I'm going to discuss is going to be how the policies around the country have taken up this topic or have tried to take up the topic of GHG emissions from energy storage and what the experience has been so far and the lessons we've learned from that from those policy discussions. So again, I'm Ted Koh, Director of Policy from STEM. For those of you who are familiar with STEM, STEM operates the world's smartest and largest digitally connected energy storage network. We are the leading developer of customer-sided or behind-the-meter energy storage projects for the commercial and industrial segment. Most of the information on this slide is not particularly relevant today, except for the two pieces of you see on California SGIP and the Clean Peak concept, which are the two policies that I'll be talking about today. And for California SGIP, we probably have the most device hours in operations of any company that has installed energy storage systems under the SGIP program. And we are the lead stakeholder in the discussions around the GHG for SGIP-funded projects. And then for the Clean Peak concept, we've been part of most of the conversations around the country around designing the Clean Peak idea, and I'll go into a little bit more detail about what that is later on. And then as people are talking about discussing how do we design Clean Peak policies to, again, reduce GHG emissions using storage. So a summary of my section of this talk and this webinar is that at the top level, a lot of the misconceptions around GHGs and storage need to be corrected, and we need to work on it as an industry and as a community to help policymakers especially understand that these misconceptions need to be fixed. The first one is that storage increases GHG emissions. So there was an article not too long ago that said, storage is dirty little secret, was the headline. And given the takeaway that a lot of people are taking away from the kind of research that Eric is doing and others have done, is that storage just increases GHG emissions, and as like the high level takeaway without the nuance behind that. And so that's the first thing we need to work on. The second one is storage paired with renewables is cleaner. That if you co-locate them and you charge the storage from your co-located solar or wind generators, that it's automatically cleaner than storage standalone. And Eric went into that a little bit in his section, and we'll go into that a little bit more about what the implications of that misperception is in policy. And then the third misconception is that the best way to make storage be cleaner, reduce emission, is to just improve the mix of the grid, the mix on the grid itself that's operating in. Whereas that's the kind of high-level takeaway, which is still looking at storage as a static device and not something you can send price signals to. So we'll get into that a little bit more. So what we want to get to through this conversation and through all the stakeholder conversations and policy making around the country is, one, storage does not increase or decrease emissions, like in and of itself. And then any assumptions you make about what storage is going to do in order to make your policy around the GHG emissions is kind of fundamentally a poor premise to base your policy on. We'll go into that. The second one is standalone storage should be treated the same as storage co-located with renewables. Again, if it's the same GHG impact, so any policies around GHG impact of storage should treat those two things the same. And then the third thing that we want to get everyone to understand or to base their decisions on is that you want to prioritize the long-term GHG benefits of your system rather than the short-term individual impacts of like a particular installation. And so instead of requiring or forcing like each individual storage installation to have a short-term operational decrease in GHG emissions, you need to look at the longer, bigger picture of what the storage as a whole will enable your grid to be cleaner. So the bottom line is, at the end of the day, is we wanted everyone to look at enabling storage to reduce emissions, and the best way to do that is to send the right price signals that will result in a long-term lower GHG grid. So I'm going to be talking about all these concepts and these ideas through the lens of the California SGIP program and then also the clean peak concept that has been getting a lot of traction and conversation in the last year. So the SGIP story. California Self-Generation Incentive Program was actually first created back in 2002, but energy storage wasn't eligible for the program until many years later. I think 2009 or 2010 was when it first started becoming eligible. And so the program started out as a relatively simple rebate program. It's an upfront rebate, dollars per kilowatt hour of energy storage capacity, and you get that up front when you install the system. And the statutory requirement of the legislation that created this program requires that all the technologies that are funded by this program need to reduce GHGs. And it's important to note that this program wasn't created for storage originally, and so the requirement to reduce GHGs applies to all the technologies, and it was really targeted more at generators like fuel cells or microturbines and these other kinds of technologies. And so this requirement was then tried to apply to energy storage later on, and we'll see how it was misapplied in a way that caused actually unintended consequences and negative consequences. So when the staff was looking to implement this, they said, okay, we understand the basic formula. Your carbon impact is going to be the difference between how much carbon you increase from charging the battery, which is, Eric went into discussion on that, is what's the marginal generator on the grid when you're charging the battery. And then you subtract the carbon displaced by discharging the battery and the marginal generator at that time, minus the round trip efficiency, like the amount of energy you lost in the round trip. And so Eric did a great job of showing that and demonstrating that with numbers, and that's the basic formula. So everybody understood that. When they came to deciding how to put this into the regulations for SGIP, they decided that instead of actually measuring the actual GHG impact of energy storage systems, they would use a proxy metric and say, we're going to set a threshold of round trip efficiency as the threshold by which you're eligible for the program, and as a proxy for whether or not you're reducing GHG emissions. So on the next slide, I'll talk about a little bit about why that's problematic. So what happens is the first problem you have is that the real formula is not just the amount you charge the battery and the amount you discharge the battery, because there's some ongoing station power or trickle charge or whatever you want to call it that is just consuming energy at the site, whether or not the battery is actually doing anything. And so your real formula has to include the energy you're consuming at all the time, as well as what's the marginal generator at each moment in time when you're just consuming with the station power. So that was the first thing that they missed in the original formula. And so then it ended up turning into a cascading series of what I would call policy mistakes or design mistakes. So first was they had to assume, okay, what time is the energy storage going to be charging and discharging in order to figure out that formula to figure out what the marginal generator is going to be at the charge. So they assumed that it would always buy low and sell high based on the kilowatt hour price. So this was a basic assumption, an operational assumption that they made to simplify their calculations, and it turns out to be completely wrong for what the energy storage installed under the SCHIP program would actually be doing. And there's a couple reasons for that, but one of the main reasons at the time was that energy storage installed behind the meter in this program was not doing energy arbitrage based on the retail rate. It was doing peak shaving, demand charge management, which isn't based on the kilowatt hour energy rate, but it's based on obviously your demand charges. So taking that assumption, they then said, okay, let's assume the marginal emissions rate during low and high price intervals. This again is wrong because they took the marginal emissions rate of what they thought the generator would be when prices are low on the California grid, and then what they thought the marginal generator would be when prices are high, which would line up if the prices that the storage was reacting to were the wholesale energy prices. But because these systems are behind the customer meter, they're actually reacting to retail energy prices, and those don't necessarily line up with the wholesale energy prices and the marginal emissions rate. So those numbers, those assumptions, and the numbers they assumed for the marginal emissions rate was automatically wrong also. So going with those two assumptions, they then said, okay, we're going to solve for this RTE and say, what does the RTE need to be so that your CO2 is going to be 0 or negative? And then set the threshold and say, okay, any technology that wants to get an incentive with SCHIP needs to have this RTE. So that was, again, a mistake because of the assumption. It's all based on your assumptions. The problem is then that later on the policymakers then compounded this by setting some regulations in the demand response program which referred to this same RTE metric as an indicator of whether or not storage is actually increasing or decreasing GHG emissions. And so you see how it's kind of cascading on as more and more regulations were brought on to address the topic of storage and GHG emissions. What ended up happening is that the evaluator for the SCHIP program later on came back and concluded and actually put on paper finally that RTE is not a valid GHG threshold metric. The RTE number the threshold they set, which was 69% or so, is not a valid metric. It just ends up being a false indicator because you can be more efficient than that and still increase GHG emissions. You can be less efficient than RTE and still decrease GHG emissions based on your operations and based on whatever the marginal units on the grid are. And so the threshold value itself became meaningless. And then what ended up happening was that when that report came out, some of us went back and did some more modeling and said, okay, if we had all of our systems that were going to comply with that RTE threshold, it actually turns out it actually forces an increase in GHG emissions than what we would have done if we hadn't been forced to comply with this false threshold. So this is the policy implications of the basic assumption the basic starting assumption of this whole thing was we're going to assume you're going to buy low, sell high, and that's how you're going to operate. And so we're going to base our rules on that. And so that fundamental assumption is a very poor way to base your regulations on. So the conclusion after we came up through all this, the California Public Utilities Commission created a GHG working group to focus on this, GHG and storage. And the conclusion was what you would expect. Is like what you really want to do is instead of assuming operations for energy storage, making any assumptions about operations, is to give energy storage the actual price signals associated with GHG that would have energy storage operationally reduce GHG emissions. So the next slide, I'll go into the next big thing that we want to correct and the implications for this particular myth. And Eric alluded to it very nicely and did that explanation very nicely about how solar plus storage, from an operational point of view, just because you're charging your storage device from co-located solar or wind, doesn't mean you have any different emissions profile than just storage standalone, because it's still based on the marginal generator. And so I'm glad Eric described that because I've had to try to convince people of that and make that explanation many, many times. But the problem is that this particular myth is really persistent around the country and in a lot of policymakers' minds. So again, using the SCHIP example, a year or two ago, the SCHIP decided that they needed to go to a lottery system for the incentive. So there were so many people, so much demand for the incentive that they couldn't do kind of a first come, first serve, here's your incentive program anymore, so they decided to go to a lottery system. And so everybody who came in around the same time would then go into a lottery to see who got the incentive. One of the problems with that was when they decided to implement this lottery system, the commission just said, okay, we're going to give solar plus storage priority in this lottery, just because based entirely on this particular myth that it's going to do better for GHGs if we get more solar plus storage installed out there. And to be fair, I mean, this was super intuitive to people. This is what people thought, but there was no analysis, there was no record, there's no even debate about this when they put this in place. So what that ended up happening was the next time the lottery opened for the SCHIP program, a lot of standalone storage got blocked out of the incentives, at least the first level of incentives, when actually this is counterproductive to your program, because ultimately, in a lot of ways, standalone storage could actually better meet a lot of the program objectives of the SCHIP program than solar plus storage in some cases, and has the potential to reduce more GHGs than even paired. And that discussion is a much longer discussion, but it's just a recognition that your consequences of these of making these decisions based on these misconceptions can have definitely negative consequences to your objectives of your policy and your programs. So the myth does persist. We've had stakeholders in the SCHIP program say that you need a different RTE threshold for solar plus storage because the charging side of it is completely zero emissions. But then you had a report come out again from the evaluator of the SCHIP program that specifically says no, this is not any different. But then even after that report came out, we were still struggling within the SCHIP program to educate everybody to make sure that we don't design rules around that priority, and that priority still exists in the SCHIP program. And then you're seeing policies around the country where incentives or programs or like value stacks or anything around renewable energy or around storage are valuing or prioritizing solar plus storage over storage standalone, again, for this reason. The one caveat to this whole thing, and Eric alluded to it a little bit in his talk, is that while you can't give solar plus storage more credit for reducing GHG emissions from an operational point of view, there is this concept of what we call the build margin, which says that if that solar or wind or whatever was not going to be built without the storage, then you can give storage credit for bringing new clean energy onto the grid, and that's what we call the build margin. It's like the marginal emissions benefit that you've induced by enabling more clean energy on the grid, and that's separate from kind of the operational impacts, the real-time marginal emissions impacts that you have by storage operations. But it's something that is certainly worth considering and something that should be built into policies going forward. So again, the long-term GHG benefits. I'll go a little bit fast. I know this is taking a little bit of time. So again, long-term GHG benefits. I'll gloss over this really quickly. is the ability for storage overall to help deal with what everyone's familiar with, the duck curve, and help reduce GHG emissions by enabling a higher penetration of renewables on the grid. And so this is the way how we should look at what storage can do rather than storage specifically, each individual installation doing that. I'll jump through that really quickly, and then we can, if there's questions on that, we can go further into that. Then I'm going to briefly or quickly go into the clean peak. Again, I'm running a little short on time. For those that are not familiar with the clean peak, it was about the original concept was evolving the RPS. As you're getting to higher and higher levels of clean energy, you're getting kind of diminishing returns in terms of your GHG benefits as you get to higher and higher penetrations. So if you could shift that around, you could get to higher penetrations of clean energy and still get the GHG and cost benefits for the ratepayers. So so the idea was that let's set up a system or mechanism by which you are shifting where you're shifting from off-peak times to peak times. Hello, am I still on?
Yeah, we hear you, Ted.
Okay, sorry. There was something strange with the conference line. And so the idea was let's have storage shift clean energy from the off-peak times to the peak times and thereby reduce GHG emissions. The first mistake that people make in designing this policy or legislation has been that, again, if you have an existing solar plant and you add storage to it and shift that solar plant's production from off-peak to on-peak, then that's 100% clean. And Eric demonstrated that that's not exactly true. So what ends up happening is if you pay people to do that, you're potentially overpaying for GHG reduction. The second mistake that people make in designing this policy is that standalone storage does not qualify, and saying that that it's not shifting clean energy if it's just charging from the grid. And so that misperception has potentially kept standalone storage out of several of the policies that are going on. And then it has a direct policy impact. It's like the misperceptions around standalone storage ended up creating a lot of resistance and some strong voices, even from the environmental advocates that kind of fighting against standalone storage in this clean peak ideas because of this misperception around standalone storage and its GHG impact. So I'll kind of go through. There's ways and mechanisms in which to account for these kinds of mistakes and design problems. But we can get into that as we get into, if you want to get into a deeper conversation around clean peak design. So finally, just in conclusion again, we want to get everyone to, storage is not clean or dirty by itself. Changing the grid conditions that storage operates in is not enough by itself to help reduce emissions from induced by storage. The best way to do it is to actually make sure that you have a price signal come through. And a price signal associated with the GHG. A marginal emission signal, a price signal associated with marginal emissions, can help direct real-time storage operations. And then another kind of price signal, which is compensation for helping renewables integration, can help storage enable a long-term cleaner grid. And that's it for my presentation.
Great. Thank you so much, Ted. In the interest of making sure that all of our speakers get sufficient time, I'm going to just move on now to our final presentation from Elizabeth Knoll, Deputy Director of Congressional External Affairs for NRDC's Climate and Clean Energy Program, to offer her perspective. Elizabeth?
Thanks, Jason. I will try to keep this brief. I don't have slides, and I wish I do now because you'll have to look at my face for the next few minutes, but I just wanted to say thank you, and at the outset, this is a new space for NRDC to be engaging in, and we're very interested in the opportunities that energy storage presents to help us reduce our carbon emissions. And so I just want to offer to those on this call that we would love to collaborate with folks and to, every time I listen to these presentations or we're running our models, we're learning more about how energy storage and the right price signals and the right policy design impact exactly what the market takes up. So, we're really interested in making sure that we're crafting policies in the right way, and I'll get into that a little bit in our remarks. So just kind of as a baseline for NRDC, like when we look at technologies and look at what solutions we want to advocate for to achieve our environmental objectives, we try to approach this from a tech-neutral place. We really want to advance climate solutions with a proven track record, those that can be done so affordably, those technologies that can be scaled, and those that are safe. And when we talk about safe, it's we're not looking to trade one environmental impact or emission for another. So, and when it comes to energy storage, we see this as one of these transformative technologies that can really facilitate climate solutions that are affordable, scalable, and safe. We see it as something that can provide flexibility to meeting shifting patterns of electricity usage. We see it as a solution to complement renewable resources and facilitate greater growth and rapid reduction in carbon emissions, and provide solutions for like emergency power in the face of disasters, which we feel like we're going to be seeing more of as the climate challenge continues to escalate. And I think it's interesting the presentations that were given. They were really great and really helpful in unpacking the storage, and I think we can all agree that policy matters, and NRDC is really in setting the right price signals and the right policy designs really matters in how energy storage is deployed. And here at NRDC, we're really focused on the appropriate state and federal policy to continue to help bring down the cost of storage, to continue to improve the performance of technologies, and develop other types of storage that have the potential to help us effectively meet our evolving electric needs. And this includes everything from R&D investments to the right policy designs and carbon price signals that can help facilitate that. So, we're looking at everything from the FERC rule and how that will help, RTOs provide guidance to integrate storage. We're looking at it in the context of state renewable portfolio standards and the opportunities there. And again, at the federal level, things like the tax credits that have been very transformative for wind and solar technology deployment, and also, the appropriations in the Department of Energy's R&D portfolio. So those are some of the areas that we're focused on from a policy perspective. And for the purposes of this call, I would say, two things that we're watching really closely with respect to energy storage, and they were both touched on in the previous presentations. But the first one is the policy and market structures that actually are driving emissions reductions. I think what we saw in the previous presentations really drove it home for me that you can get either outcome, and so really the policy design matters a lot in making sure that we're incentivizing the right behavior. And then the second thing that we're watching closely is making sure we're looking at the full spectrum of energy storage to meet our energy needs efficiently and affordably. And this is everything from daily storage needs to seasonal storage, monthly storage, et cetera. So I'll just dive into that just a little bit more to help you understand what I mean by that. And on the first one, when it comes to the policy and market structures, they need to be carefully designed to help meet our emissions reduction goals. The recent analysis like that Eric pointed to, have demonstrated that cost-optimized storage will increase emissions in coal-heavy regions. But, as he suggested, and as we all know, this isn't a problem that is specific to energy storage, but rather one of market design. So, as NRDC approaches a lot of our policy design issues, it's really around this idea of sending the right price signals to help us reduce carbon emissions. And if we get those right, that we think energy storage can really be accelerated and deployed and is going to benefit from having the right emissions targets. And different regions are tackling this differently. We've had some internal conversation here at NRDC, and I'm sure if folks on the phone are aware, we work very deeply in states like New York and California that have very different carbon goals and portfolio standards and different guiding legislation than that in MISO or the Midwest. So I think acknowledging that it may not be a one-size-fits-all policy perspective, but that really we want to ensure that these incentives are aligned with the emissions goals that we're seeking. And then on the second point, I'll just close out here by saying that we're looking at the need for significant investment in the full spectrum of energy storage. That will allow a diverse set of technologies to overcome market barriers and meet our needs. We've seen significant investments by DOE to increase the performance of lithium-ion batteries. But as we look forward, it would be a shame to stop there. Research into long-duration storage that can help be transformative on a larger scale, is something that we need to keep an eye on. I agree that we need to keep that long-term greenhouse gas emissions trajectory and understand the use cases of storage and how different types of storage can help meet certain energy needs and different use cases. So that's keeping a broad and open mind when it comes to what we need to be investing in, I think is something that we're really interested in. And I'll give two examples of just recent work that NRDC's been working on. One, we've worked for a couple of years now with the rural electric co-ops on what's been known as the Community Storage Initiative that was really born out of a conversation of how co-ops were deploying water heaters as storage devices, if you define storage broadly, to help meet their demand needs more affordably. There was a report that was done by Brattle a couple of years ago called The Battery in the Basement that notes that how this opportunity can help us tap into and leverage energy more efficiently and affordably. And similarly, we saw, I think in the last few weeks, a study by Lawrence Berkeley National Lab that looked at kind of how electric vehicles can help leverage, meeting storage demand or storage mandates in California in a more cost-effective way, and how utilizing storage in the electric vehicle scenarios can help you displace both the oil and gas burns in a combustion vehicle, but also help us meet our energy needs more cost effectively, and how that can help even beyond a stationary energy storage approaches. So just a little bit of how we're thinking about leveraging all of the opportunities that storage can present to help us, reduce costs, reduce emissions, and meet our climate and carbon objectives. So just in closing, we're working closely again, with the Department of Energy and with members of Congress on the R&D front, really wanting to make sure that as we look at the opportunities that energy storage presents, that we're helping to validate that with good analysis and good solutions and good technologies. And then, opportunities like tax credits and other policies at the federal level, and also in our state and regional work to help to make sure that storage is being valued appropriately, and also being incentivized to help reduce emissions. So I am going to leave that there and look forward to the questions and discussion.
Great. Thank you so much, Elizabeth. And this is Jason. I'm pleased to tell you all that we're going to keep the webinar going for at least another We're going to keep it open until 2:45 p.m. Eastern Time, just so we have at least a little bit of time for questions. To our presenters, please stay with us if you can for these next few minutes, though we understand if folks have to run. But now we're going to open up the floor to questions for any of our presenters. And while we're waiting, and remember, you can submit questions using the chat box on the left side of your screen. I'm just going to tee off one very quickly for folks, which is, hearing, this is sort of to get back a little bit to this, I think, discussion about sort of additionality. There's this understanding that, as Eric kind of points out in his study, if you're going to be adding more zero greenhouse gas emissions generators like renewables to the grid, that's going to be ultimately offsetting any impacts from additional storage. And Ted is sort of, you're talking about how, there's obviously this sort of way in which accounting that's premised on a project basis obviously makes it trickier, but you have this concept of a build margin, the idea that, again, sort of additional renewables does enable you to gain the greenhouse gas reduction benefits from storage. I think the question I have is, how do we deal with that, whether it's in the modeling, in the communication, because there seems to be a tension here between sort of systems level thinking about storage and greenhouse gases and project level accounting effectively.
So I would say that you're looking at the whole system level. You're looking at the mechanisms you have in place for the build margin ideas. Is right now you have a kind of a weak mechanism, not a weak mechanism, but a kind of a mechanism with RECs and renewable energy credits that's itself a kind of a proxy for future GHG emissions. But if you look at your long-term kind of IRPs and planning for your mix, modeling for your mix of the grid, you can look at what services energy storage needs to provide to enable that higher penetration, like what kind of ramping and peak shaving or soaking up curtailment would help. All those kind of duct-related services, and then if you can do that, then you can price those services accordingly to their GHG benefit, and that would then give the storage the kind of compensation for providing the GHG reduction in the long term than it could provide.
Yeah, I guess I would add to that. I don't disagree. I would add, like, as a person who does this type of modeling, that indirect effect would be really hard to model and measure. So if somebody came to me and told me they were absolutely certain of how much new solar will be put onto the market for every megawatt hour of storage that you put into the system, I probably wouldn't believe them. I almost think it's such a hard problem. I'd rather see energy storage, supported through mechanisms that support more directly measurable benefits or market failures in some case. I'd rather, for example, see government support for storage because it is a valuable emerging technology, which is something hopefully everybody could agree with. And there's a market failure that emerging technologies tend to be under-supported in the marketplace, than for something that's kind of indirect and hard to measure and probably isn't quite that huge anyway.
Got it. Well, and to follow on that point, are the policies here really just as simple as put a price on things like greenhouse gas emissions and deploy more renewables? Is there something more specific we should be thinking about in terms of public policy to ensure storage is contributing to reducing greenhouse gas emissions? Obviously, this clean peak standard concept Ted mentioned is sort of floating around there, but is there more to it than just that?
Well, I guess I can say, as an economically minded person, putting the correct price on things and then letting the market run oftentimes can, at least in theory, be very helpful. One of the things that's kind of come up in this discussion that through the whole hour that I think we should say explicitly is that for things like renewable energy, you don't need correct carbon pricing to get reasonably good outcomes, right? If in the absence of a carbon price, you can subsidize renewables and you'll get the emissions benefit. In the absence of a subsidy, you can have a renewable portfolio standard and force renewables into the market, and you'll still get the emissions benefit. Storage is sort of a new thing, so we need some kind of new policy where just putting storage into the system won't necessarily reduce emissions benefits, which is why all of us have been talking about, like, how do you change the markets, how do you change the incentives to get storage to actually do something more valuable emissions-wise. I think anything that moves us in that direction, a price on carbon would be great, but even having a price signal that storage can follow in order to operate would be a fine substitute.
Yeah, this is Elizabeth. I would just add, I think that's right. That would be our preference as well. I think the other acknowledgement is that that's harder in some areas than others. We've noodled with even just kind of the competitive procurement approach of making sure that we're at least evaluating the value of a storage solution or a solar plus storage solution versus a natural gas option or something like that, to really just make sure that we're doing the full evaluation. But do think that that the price on carbon is simple in the context of depending on how you define simple. So.
Sure. Well, and this is Jason. I'll just add my own 2 cents here. I also think that there's the broad sort of policy levers that we're talking about, and then there's also looking at like the specifics of the grid you're in. And I think an interesting example is, for example, places where you have local constraints, right? Where you might not have curtailment from a system standpoint, but from a local standpoint, you might have some sort of policy that forces curtailment. And then something you're not talking about necessarily a price on carbon or some sort of renewable energy subsidy per se, but you're starting to look at how those local constraints might be, for example, resolved to avoid that curtailment. Does that strike you all as something relevant to be thinking about as well, or is that sort of secondary to this larger issue of sort of the overarching public policy approach?
I can jump in on that one. This is Elizabeth again. I think I would agree, and that kind of gets to a little bit of what I was saying about also looking at the broad spectrum of storage opportunities, and that there's going to be a variety of use cases, and wanting to make sure that we're developing the solution set that's going to help achieve the energy needs. And those could be, a various assortment of storage opportunities that you'd want to deploy, be it from a local energy need demand side, or from seasonal variation, or a whole host of what consumers are demanding, what the state is requiring, those kind of things. So I tend to agree that it does need to be taken into consideration as you're developing the policies.
So again, we are open for your questions here. So we have time for another couple more. Another question here is, certainly, we're focused on the greenhouse gas emissions question. Other studies have noted the impact of reducing, for example, NOx and SOx by using storage in place of certain thermal generation. To what extent could addressing those kinds of air quality issues achieve similar goals of greenhouse gas reductions in the use of storage?
So this is Ted. I would say that as you can include that into the kind of, this goes back to the clean peak ideas, and some of those studies have been focused around the idea that if you can use storage to reduce the dispatch or even eventually retire some of the dirtiest peaker plants, then you should implement policies like a clean peak type style policy to target those particular plants. And so that's certainly possible, and it's an idea worth exploring. And it would just, I think, would just add to the value of the whatever mechanism you're creating for helping storage reduce carbon emissions. It would just add more value to that mechanism, and then would make it more economical for storage to do it.
Yeah, I agree. This is one where, like, the New York Energy Storage Roadmap, it includes NOx and SOx from decreased usage of gas peakers as a large benefit. And one area where this has been, exactly what Ted was saying, it just adds additional value to that storage. And from our perspective, we've been collaborating and working with the environmental justice community and impacts where there's really like localized air quality impacts. And this can also have huge benefits when you're trying to address those environmental justice concerns for specific communities.
And I should know, this is, oh yeah, go ahead.
Oh, yeah, I was just going to say, we actually, the papers that I talked about here, I only showed the carbon analysis, but we actually did the same analysis for NOx and SOx, and we did find sort of what you're describing, that basically in regions that don't really have any coal, New York, California, New England, or effectively none, that storage was actually reducing the NOx and SOx. If you have coal, in the Midwest, well, coal has a lot of NOx and SOx emissions, so you actually still increase them. But and we're working on, here's a teaser, an advertisement for the future, an analysis that kind of integrates all of these and the value of reducing emissions, the local pollution damages, health damages, and tries to figure out how one should operate storage and what the net benefits could be of a sort of operating storage to both make money and improve human health. So.
Well, that's great. And I should note, speaking of previews, for all of you who are joining us today, this webinar is second in a series that has been focused on a lot of sort of the environmental issues around energy storage. And ESA is planning a future webinar on environmental justice issues and energy storage to come in September, so stay tuned there. It does look like, unfortunately, that's all the time we do have on today's webinar. So I want to thank Eric, Ted, and Elizabeth for their presentations today. I also want to tell you all that we have another exciting webinar teed up for next week. So please consider joining us for financing, funding, and a federal agency. In addition to lots of alliteration, you're going to have representatives from 3 U.S. Department of Energy offices, ARPA-E, the Energy Investor Center, and the Loan Programs Office, to discuss current and upcoming financing and funding initiatives and opportunities available to the energy storage sector. That is next Thursday, August 30th, beginning at 2 p.m. Eastern Time. And if you have any questions regarding any upcoming events or webinars for ESA, or would like to submit an idea for a future webinar, please don't hesitate to reach out to us at education@energystorage.org. And with that, thank you again to our presenters, and thank you all for joining us today in this important conversation. Enjoy the rest of your day, y'all. Take care.